Okay, so this first problem, we're graphing y equals 2 to the x power. This is an exponential function, and you can set these right up on your graphing calculator, and then that'll give you always a sense, if you forget how these things work, to think about some of the intuition here. Just press the y equals button, 2, and then to the power of, that's this button over here, x, this button right here, and press enter, and you're done. When you graph it, you can see how this graph kind of grows, and they grow amazingly fast. The basic idea is that, right, as x gets into the negatives, your number is reducing, approaching 0 but never touching it, and as x is increasing, your graph, when it's a positive base, and when the exponent is positive, is actually increasing, right? So we can mess with the base and the exponent, but if all things are positive, this is what you'll see. And if you want to see what happens when, for example, your base is negative, we can just hit second insert and then play with this function a little bit. Now we have a negative function, and you'll see how the shape of it changes. So, you often are given questions where you're asked to analyze these kind of functions and analyze how different parts of the function being changed can change the shape of the function. So you can play around with that in your graphing calculator to kind of gain some intuition. Now specifically here, they want us to graph this by hand in this interval where x is larger than or equal to 1 and less than or equal to 3. So a good approach when you see that is just to pick the integers in that interval. So when x is -1, when x is 0, when x is 1, when x is 2, and all the way up to and including 3. So what you can do to figure this out exactly is set up a table. We have the x values here, -1, 0, 1, 2, and 3. And then over here you'll have the y values, where y is 2 to the x. So plug -1 in. We have 2 to the negative first. Remember, that's 1 over 2, or 1 divided by 2. 2 to the 0 power, where x is 0, is equal to 1. 2 to the first is equal to 2. 2 to the second is equal to 4, and 2 to the third is equal to 8. So these are your points, right? Your first point is going to be -1, 1/2. So we plug that in. -1, let's say this is the y-axis 1 and 2 and 3. So we have -1, 1/2 right there. 0, 1, right? When x is 0, y is 1. When x is 1, y is 2, right? When x is 2, y is 4. When x is 3, it's 8. So count there, 1, 2, 3, 4, 5, 6, 7, 8. So right here. And then you would just connect this right here. And you can just graph the interval right there. It should be a little bit smoother, I hope, when you draw it. But right, this graph will keep extending, but you only need to draw it there. I just want to talk for a moment about, again, what's happening here. Think about why this approaches, right, 0. But it approaches 0 but never touches it. You can think about a couple of extreme cases, right? If we have -2, -3, -4, that means this is when x equals -4, y equals 2 to the -4. And that's just 1 over 2 to the 4th, right? Or 1 over 16. Small number. But jump ahead further down. Let's say you have eventually ... right? You reach x at a -100. Well, this is going to equal, when x equals -100, you get y equals 2 to the -100, and that's 1 over 2 to the 100th, an enormously tiny number, right? Oops. And here, I guess, let's see if we can model that in the graphing calculator. If you have 1 divided by 2 to the 100th power, right? Here, it's about 7.8 times 10 to the -31st. So that's, right, that is 0.00030 times, right, 7/8, a tiny, tiny decimal, but not 0. So in fact, we get closer and closer to 0 but never hit it, because these negative exponents give you smaller and smaller decimals. It's dividing by the base over and over, dividing 1 by the base over and over and over again. So we have, when x is -4, it's 1 over 2 to the 4th, and x is -5, we have 1 over 2 to the -5th, all the way on and so forth. In the reverse, and if we were to extend the line here to the right, which we're not doing in the problem, but if we did, you can imagine the rate of growth. It grows exponentially, and you can see how steep it would get. In fact, I should draw this a little bit better, right? Just the steepness will go incredibly fast. Already at 4, when x is 4, we're off the grid to 16, double in height, maybe right up here. Okay, so let's keep going. Okay, so we see lots of problems where looking at equations with exponential growth. And we'll talk about the basic approach to it, which is that y is going to equal a times b to the t, oops, where a, let me fix that, it doesn't look very good, a times b to the t power, where a represents your initial value, right? B represents your change, right? How much is growing, how much is your value increasing or decreasing each year, and t represents the time period, and specifically the time period of the growth. So if it's every year or whatever, you had to calculate how many time periods are passing, which we're not going to get into right here. But there's a logic behind this. You don't need to memorize it. Let's look at this problem. There are 64 teams to compete in a tournament. After each round, half the teams were eliminated, which equation represents the number of teams after r rounds. So our time period is rounds here. But the logic, I think, when I try to rediscover this logic and I forget everything we're talking about when I'm doing this, we'll have r equal the round number and t equal the number of teams left, just like they have in the equation. So first we start with 64, right? So at the start, when r is 0, there are 64 teams available. And then with one round, there will be 32 teams because we're halving them. After 2 rounds, there will be 16. 3 rounds, there will be 8. 4 rounds, there will be 4, right? We're halving each time. 5 rounds, there will be 2. 6 rounds, there will be the 1 remaining team. So there's this idea that we're halving 64 each time. So you can think of 64 when there was 1 round, right? You multiply 64 by 1/2 once. When there's 2 rounds, you multiply 64 by 1/2 twice, really, times a half to get 32, times a half again. When you have 3 rounds, you multiply 64 by 1/2 to the third, because you're halving it 3 times. So in general, you could say you start off with 64 teams, and you're halving it how many times? Well, r times the number of rounds. So as another example, when r is 5, you have 64 times 1/2 to the 5th. And 1/2 to the 5th is 1/2 times itself 5 times, which is 1 over 32, right? So we get 64, just testing this formula out, times 1 over 32. And that is equal to, right, 2, because 32 goes in 64 twice. And that's correct. After 5 rounds, there are 2 teams. And it even works for the 0 case, because when r is 0, right, you have 64 times 1/2 to the 0. Now 0, 1/2 to the 0 power is 1. So it would be 64 times 1. And that's true. There are 64 teams at the start when there are 0 rounds. So this can be shown here, right? 64, t equals 64 times 0.5 to the r power, or to the amount of rounds that we have. So, there's these equations, and we have these rules, but there are, of course, reasons or logic behind them. So we can always find a way to think about them. Okay, let me just patch this up. Here, I'm cluttering up my space. Sorry about this. Okay. All right. So in this next one, they're giving us the equation, and they're asking us to kind of analyze it. They say A equals 21,000 times 1 minus 0.12 to the t power. And before I even read any further, I'm going to simplify this, because 1 minus 0.12, that's just 0.88. I just think of 100 minus 12 as 88. Same idea. So when this number is a fraction, right, this is called exponential decay. It just means that when you multiply by this fraction, right, if you multiply 21,000 by this fraction over and over again, you're reducing the size of the object because you're multiplying by a fraction. As long as 21,000, of course, itself is a positive number. So let's look at this as an example. Before we get into the answer as well, let's just see what's happening. So if t is equal to, say, 1, right, it would be 21,000 times 0.88 to the 1, which is just 0.88. So times 0.88, we get 18,488. Now, if we want to figure out what this is as a percent of the original, we can do that number, so hit second answer, divided by 21,000, right? It's, of course, what is it? Well, it's 88% of the original. So we lost 12%, right? If we took 21,000 and we multiplied it by 12%, 0.12, that's 2,520. If we take 21,000 and subtract 2,520, we get 18,480, which is our new value. So each time, right, we're taking 88% of what we had before. But that means if you have 88% of what you had to begin with, you've lost 12%. Think of the example: if you have $100, and I say take 88% of that. Well, to do that, you multiply it by 0.88, and you get what? Well, $88. Well, you had 100, now you have 88, you lost 12 out of 100, or 12%. The same idea right here, just we're dealing with exponents. So if t is a larger number, like 3, you'd have 21,000 times 0.88 3 times, right? And that would just mean you lost 12%, and then another 12% of that, and then 12% of the new total, and so forth. So using 12% of 12% of 12%. So this is called exponential decay. We're losing value at a rate of 12%, right, for each period. Especially with the wording they give us, they first of all say, is it exponential growth or decay? So again, we're multiplying by a fraction, it's decay. And the rate of change, right, that means how much did your value go up or down by? If it was what is the result as a percent of the original, then you say 88%, because it's 88% of the value before it, right? You have 21,000, then you have 18,480, which is 88% of the beginning cost. But you look at the change of percent, you add or subtract an amount. This next problem, we've got y equals 3 to the x, and that was to graph it in this interval, -1 to 2. So we set up a table with our x and our y values. Now y is equal to 3 to the x, right? That's the equation. So for the y value, I'll just write 3 to the x. So if they give you these x values right here, I would just choose the integers, -1, 0, 1, 2, and that's it. Plug these in, so we have 3 to the negative first, right? That's just 1 over 3. And then 3 to the 0, which is just 1. And then 3 to the first, which is 3. And, sorry, not 2. 3 to the second, which is 3 squared, or 9. So here, I would set up my axes, right? Y-axis, x-axis, and they want this in the interval of x is -1 up to 2. So we're just going to graph that. So here's -1, 0, 1, 2. So we plot these points. We have -1 when it's the value of x, and y is 1/3. So here, since we are dealing with a third, it's a little difficult on this scale. I can't actually, I don't have room to break because I'm going all the way to 9 and thirds. I'm just going to estimate. And I want to put this little point right here, and I would label it as -1, 1/3. So it's clear. And then I have 0, 1. So 0, 1. I have 1, 3, 1, 2, 3. And then 2, 9. So 3, 4, 5, 6, 7, 8, 9. Now here's the thing, when you graph this, you don't want to show a line between, you want to show this curvature, because the exponential function grows so fast. And if you need to extend it, you can. Just make sure you don't cross 0, because as it goes past -1, it will approach 0 but never hit it, because you get these tiny, tiny fractions, but never actually 0. This next problem, we're looking at this idea of depreciation, or losing of value. So we look at exponential decay, right? Decay being the loss of a value. So we're losing 4.5% annually, and we start with 12,500. What equation can we use to determine the value of the car after 5 years? So think about this. We start with 12,500. In the first year, we depreciate by 4.5%. So 4.5%, that equals 4.5 over 100, right? Divide by 100, you move your decimal to the left twice. So turn this into a decimal, you get 0.045. So every year we lose this much. The idea being then that your new value is always 955 of your original value, or 95.5%. There, the idea is that 4.5% plus 95.5%, that equals 100%. So we're always taking into account, when I look at 95.5%, I knew to use that because we lost 4.5%. That means we have 95.5% of our original value. Now, if that doesn't make sense, think of a simpler situation. If you have $100 and I said to you, you lost 15%. Okay, well, that means you lost $15 and you'd have 85. So the idea is, oh, you lost 15%, that means you have $85 now, and 85 out of 100 is 85% of your original. So there's this balance between the loss and what remains. With this process, if we're not recognizing that, we can just calculate. So we can do 12,500 times 0.045 or 4.5%. What's going to happen? Well, let's take a look. 12,500 times 0.045, and you get this number 562, right? 0.5. Now, if you want to know what this is as a percent of the original amount, right? What would you do? Well, if we take this and just divide it, so press divide 12,500, we can confirm that, oh yes, that's 0.045. But if we go back to our original spot, I'm going to undo that division and multiplication. Here, you can ask yourself, well, you have $562.5 that you've lost, right? So how much do you have? So you do 12,500. You've lost 562.5 or 0.045%, 4.5%, excuse me. And that's this number. Now this is where the 95.5% is. If you divide this by the original, that gives you this decimal, 0.955, times it by 100, and we have a percent. What I'm doing here is, again, I first figured out how much I lost. So, and then I figured out, well, this new amount that I have, what percent is that of the original? And I just did that by dividing this new value by what I started with. That's just another way to connect it. So again, this right here, first you multiply it by 0.045. That tells you how much you lost in 1 year. Then you say, well, 12,500 minus this, that's how much I lost. What's my new value? Well, that's 11,937.5. Well, this, if we take 11,937.5 and divide it by 12,500, we get 0.955, which is 95.5%. Why am I showing you all this? Well, it's the key to understanding how to write these exponential decay functions, because when you take 12,500, you can, instead of multiplying by 0.045, right, and then finding out what percent remains, right, because that's what I'm doing right here. After 1 year you have this amount, you could just say 12,500, right, instead of subtracting 4.5% and then calculating the new value, just multiply from the beginning. Multiply 12,500 by 95.5%, or 0.955. So after 1 year, you would have 11,937.5. The next year, you lose 4.5% of that value. So you can take 11,937.5 times 0.955 again. And what would that get you? Well, 11,937.5 times 0.955 equals this number, 11,400.3125. But here's the awesome part. Realize that we multiplied the original value, 12,500, by 0.955, and then multiply the result by 0.955 again. So we could have just done 12,500 times 0.955 twice, or 955 squared. So after 2 time periods, we multiplied the original amount by the percent that remains. So here we can just pick this formula, right? For 5 years, we would do this 5 times. And in general, you could say, oh, this number 2 represents the time periods that have passed. This is the original value, and this percent right here is the percent of decay. So it's not how much we lose each year, but how much remains, in fact. So, and if you don't like that wording, the last thing I can offer you here is to think of this as the 100%, or 1, minus 0.045. So that's an exponential decay. You always get this number in here by starting with 1 and subtracting the percent that you're losing. Alright, hope that helped. Let's go to the next one. Okay, so in this one, it's another exponential decay problem where you're losing value. Let me just clear these spots off for you so you can see. Okay, fill these back in, patch them up. Alright, so here, Cassandra bought an antique dresser for $500. Okay, so the starting value is $500. And if her dresser increases, not decay, but growth, 6% annually, so we have an increase by 6%. What will the value be after 3 years to the nearest dollar? Okay, so think about it this way. You have $500, and when you increase by 6%, it's 106% or 1.06 of your original value. If you're not convinced, you can say, oh, well, to find the new value, I'd just do 500 times 6% and then add the original 500. Let's just try that. So 500 plus 500 times 0.06. Alright, so it's like 500 plus 6% of 500 is 530. But if we take 500 and multiply it by 1.06, we get 530 in one step. The idea being that you can add these two because it's like 1 500 plus 0.06 500 is 1.06 or 106% of 500. Why am I telling you this? Well, each year that passes, this is going to happen. So the first year is going to be 500 times 1.06, all right? And then the second year is going to be that result, which is 500 times 1.06 times another 1.06 of that, or 500 times 1.06 squared. Over time, it'll be 500 times 1.06 for 3 years, 3 times 1.06 times 1.06. Or you can think of that as 500 times 1.06 to the third power. And in general, you can think of this growth as this number being your starting amount, this number being your growth rate, and this number being the time periods that are passing. So let's figure this out. We've got 500 times 1.06 to the third power. Oops. So I stuck here as an exponent, so fix that, see if it works. Oh, it worked anyway. 595.508. So they want us to the nearest dollar. Let me go back. So we round up to 596, or choice 3. In this next one, we have a bank with a 3.34% interest rate. So 3.75 interest rate compounded annually. So that means that if you start with $5,000, right, after the first year, you'll gain 3.57%. I like to think of that as a gain of 103.75%. So because you have your original 5,000 plus 3.75% of that. So 103.75% is our total gain. To get that as a decimal, we just divide this by 100 or move our decimal to the left twice. You get 1 for 100% and then 0.0375 for 3.75%. So each year that passes, we multiply by this number, right? We multiply 5,000 by this. The next year we do it again. So, and the next year do it again and again. So for t years, right, that's our exponent, we do 5,000 times 1.0375 to the t power. Here they want to know, to the nearest cent, what will happen after 3 years. So, right, we do this by 5,000 times 1.0375, oops, close parentheses, sorry, so I don't think it matters, but okay, to the third year, yes, 3 power, okay, 5,583.86, we round the 5 up to a 6, so 5,583, sorry, look at it again, 0.86. So in general, this is your starting amount, this is your interest in growth or loss or whatever, and t is the time period it takes to compound the interest. Here it's annually, so it's just the number of years. Okay, here we have the student population at 2,000. So our starting amount is 2,000. The enrollment increases at 4% each year. So what's going to happen in 3 years? Well, we do 2,000 times 1.04 to the third power. Why? Well, because we start off with 2,000, right? And then we grow by 4%. That's really 104 or 1.04%, 1.04 times larger than 2,000. The second year, we multiply that by 1.04 again, right? And then the third year, we do that again as well. Just keep compounding. But in general, we can combine this as many times as we compound whatever we're looking at. So it's 2,000 times 1.04 times 3 compound periods, or 3 years, or whatever the amount of compound periods that pass. And that's it. So here, let's find what this is. We do 2,000 times 1.04 to the third power, I believe. Yes, 2,249, round to 2,250, the nearest whole number. All right, thanks.